Hello everyone. Well, it's time for example problems on the topic of units and calculations with physical quantities. The underlying idea here that I hope you take with you out of this class as you move into more complex calculations in your physics engineering classes through your sophomore, junior, senior year and beyond is use standard units, get standard units. It's important to understand what the standard units are in metric and US systems, and how if you use them, you do not need to think about units very much. You just need to know that you will get the standard unit. Unit systems are designed with this in mind. You need to know what the standard units are. And in the metric, the basic fundamental standard units are the kilogram for mass, the meter for length, and the second for time. In the US, we have the pound, which is not a mass, but a force. Well, good try. A force. A foot, which is a distance or length. And the second, which is also a time. As you work through other dimensions and types of things, you just need to know that the standard units are combinations of these three things in the US system and these three things in the metric system, and they have their own names. So, for example, in metric, we're going to go through a list. For force, we have the Newton. For energy, we have the joule. For pressure, we have the Pascal. For, I don't know, let's say power, we have the watt. Is there any other I really want to describe? Nothing really jumps to mind. I'll do a couple of examples here, though. For volume, we have the cubic meter. I want to point this out specifically because the way I am using the word standard here is a little different from the way, I don't know, what might be technically correct as far as what standard means in these systems. If you ask most people what the standard volume unit in metric is, they will tell you it is the liter. And that is true, but not in the context of what I'm saying. The liter must be converted to cubic meters for this calculation and my advice here to follow. Okay, any others I really want to describe? Yeah, so these are the ones that have names that are really standard that we're going to be using from mechanical quantities. There are other things that I could give you like density, which is kilogram per cubic meter, but we're leaving the realm of things that have standardized names. So kilogram per cubic meter is a mass density, yes, but it's clearly just, you know, a mass divided by a volume here, so not too much else to say. These are the units that you ought to know. For the US, we can go through the same list of stuff. So for mass, we have the slug, not the pound mass. The pound mass is non-standard, and when you see it, you should look to convert it. Let's just go down in order. For energy, we have the foot pound. For pressure, we have the pound per square inch. I'll just write it out. Pound per square inch is the PSI. Oh, wow, that's not correct anyway. Let's go back. It's got to be a combination of the standard length unit, which is a foot, not inches. And while it's true, I kind of made my own mistake here. While it's true that PSI is in use more commonly, the standard unit here is pound per foot squared, also known as a PSF. A little bit less commonly used unit, but it is convenient if you want to do calculations in the US system. All right, what do we have next? Power. For power, we have the pound foot per second. That is power. This is not, sorry, I'm just kind of looking at my list and it's kind of going out of order. I have units on the left and dimensions on the right, with a couple of exceptions, in particular this one right here. So let me rewrite that. I want this list to be consistent, so I'm going to rewrite this one. We have the slug, which is the mass unit, and that is not the pound mass, okay? Power, this is the standard unit. It is not the one that is most commonly used. Probably most commonly used in mechanical context in US is the horsepower, and these are not the same thing, okay? So in the US, we have this recurring problem that the most commonly used unit is non-standard for calculation. After power, we can talk about volume. Volume is pretty straightforward, cubic feet. And mass density would just be the slug per cubic foot. Okay? We could keep going with other units, but what you're going to see in the US system, it's overwhelmingly these descriptive units that are just combinations of the original fundamental units. Okay. Why is this list valuable? If you use units like this, you will get standard units in your calculation. If your calculation involves things on this list, and you know you're supposed to get a pressure, then you know it will be in pascals. You know. It must be the case. If you are using only units on this list, and you know your answer is a power, then you know it's going to be in pound-feet per second. You do not have to work out the units. If everything is standard, you will get standard units. So let's apply this to some calculations. I've got a couple. These are simple examples relatively. This first one is the type that we're going to be using quite a bit in this class. Just the conversions of weight and mass to different locations in the solar system. These numbers, I don't quite recall if they're accurate. I think they are, but I may have just made them up. In this situation, we have the following calculation dictating everything. Weight equals mass times the acceleration due to gravity. It's important to realize for a particular object, the mass does not change, but the weight and the acceleration due to gravity change depending on your location. So as I talk about taking an object and moving it around and doing this calculation, it's the mass that remains consistent. Mass is just a measure of how much matter you are made up of, and weight is a measure of how strongly the gravitational force is. How strongly the gravitational force is pulling on you. The strength of the gravitational force changes depending on where you are. So that's it. In this calculation, I have that my dog Otter weighs 60 pounds on Jupiter. This is a weight. And recall, whenever I give you something in pounds, that is a weight. If it's in pounds mass, it is a mass, and that distinction is important. So in this situation, I have W equals mg. This is on Jupiter, where g is 23.6. So what I can tell you is definitely my dog weighs 60 pounds, and that's equal to their mass times the acceleration due to gravity, 23.6, meters per second squared. I have a little bit of a confusion here. The rule is use standard units, get standard units, and I should probably add that is for one specific unit system. So if I take 60 pounds and divide by 23.6 meters per second squared, then I'm going to get a mass. This is a mass unit because this is force and this is acceleration, but it's not convenient, all right? It is not commonly in use. Sure, 60 divided by 23.6 can be calculated, 2.54 pound second squared per meter, but this is not standard. If I want it to be standard, I have two options. I can convert to US standard units by changing meters to feet, or I can change to metric standard units by converting pounds to newtons. Remember, pound is a force unit. If I move over, you might think that pound lines up with mass, but it doesn't, because this is a force and this is a mass. Pound lines up with Newton because they are both forces. So Let me erase all this stuff. Pound is not a mass. I will do both. So my first conversion will be feet to meters. There are 3.28 feet per meter. And if you're paying close attention, you'll notice that I've just made a mistake. I have multiplied by 1, but not the correct 1. This meter is not going to cancel this meter. They're both in the denominator. So I'll just use the eraser tool for this. So we multiply by 1 meter divided by 3.28 feet. And this is equal to 0.775. And what do we have? So this is where I'm not going to write out the units and think about them. I have converted to standard US units, so I'm going to get the standard US unit for mass. What is the standard US unit for mass? It is the slug. So this is in slugs. Pounds mass has nothing to do with this calculation whatsoever. Alternatively, I can start with what I had. M equals 2.54 pound second squared per meter, and convert pounds to newtons. There is 1 pound in 4.45 newtons. And now I'm left with 11.3 what? Well, I've converted to standard metric units, so this is going to be the standard metric unit for mass, which is the kilogram. These are my two results. They are equivalent to each other, and it's just true that 0.775 slugs is equal to 11.3 kilograms. That is true. Either one of these approaches is perfectly fine. Convert to US units and get the standard mass unit of slug. Convert to metric units and get the metric unit of mass, which is the kilogram. All right, I haven't actually answered any of their questions yet. So what is Otter's weight in Neptune, on Neptune, where G is 13.3? Well, I have the mass, so I can do this calculation. W is equal to mg. They give me the acceleration due to gravity in meters. So I think metric is going to be most convenient here. I'm going to therefore write this as 11.3 kilograms times 13.3 meters per second squared. And these are standard metric units, so I'm just going to get the standard metric unit for force, which is 150.3, the unit being newtons. That's the answer for part A. I could also have done 0.775 slugs times the acceleration due to gravity, which is 13.3 meters per second squared. But this is a non-standard US unit, so I will change it. There are 1 meter is 3.28 feet. By the way, I'm using the conversions that are up here. These would be given to you on an exam, although we're not going to have a traditional exam now, so you can just look this stuff up yourself. The meters cancels. I now have standard US units. If I multiply these out, 0.775 times 13.3 times 3.28 is equal to 33.8 of the standard US unit for force, which is the pound. And it's true. 33.8 pounds is equal to 150.3 newtons. Don't believe me? Use this to check. Cool. Anyway, these are both acceptable answers for part A. It's plausible that I would ask you specifically for the answer in newtons or pounds. So you need to be able to do both of these. For part B, they ask for the mass in kilograms and her weight in newtons on the moon. The acceleration due to gravity on the moon is 1.62 meters per second squared. Well, the mass is easy. The mass doesn't change as you move around. They ask for it in kilograms. I already know it in kilograms, 11.3 kilograms. As far as the weight is equal to mg, which is equal to 11.3 kilograms times 1.62 meters per second squared. This is standard, so I get the standard force unit. 11.3 times 1.62 is equal to 18.3 newtons, the standard weight unit. And they asked for it in newtons. Weight in newtons up here. So this is exactly right. I'm going to go ahead and, I wish I hadn't circled so many things now because it looks like I got a bunch of answers. But the answers are these three quantities. Okay. All of these are acceptable answers. This or this for part A, and this specifically for part B. So, cool. That's this calculation. For the next calculation, we don't have quite so much challenge because there isn't a relationship between force and mass, but I still want to go through this calculation. This formula, the time it takes to fill some pool, is given by the density times the volume divided by the mass flow rate, and all these things are given. I gave the density. The density is given as 1.94 slug per feet cubed. The volume is given as 2,500 cubic meters, and the mass flow rate, they did give it to us, right? Oh, there it is. 40 pounds mass per second. I can think about a way to try and work this out, but I'm not going to think too hard. My strategy is going to be convert to standard units in one system or another. So what I'm going to do is convert this to US standard units. All right? So on the bottom here, I'm going to convert pounds mass to slugs. There are 32.2 pounds mass in one slug. This cancels that. I multiplied by 1. This is good. And then on top, I have cubic meters, which I'm going to convert to cubic feet. There are 3.28 feet in 1 meter. And to cube that, I must cube the entire relationship. Of course, this is 1. So cubing it is still fine. That is still 1. But now I will have cubic meters cancel cubic meters, and I'll be left with cubic feet. And that's the entire calculation. Slug is going to cancel with slugs. Cubic feet is going to cancel with cubic feet. And I'll be left with this second spitting back up to the top. But again, that need not be considered. I'm using standard units, so I'm going to get standard units. I use standard units in the US system, so I'm going to get the US standard unit of time, and that's seconds. I'm not actually going to worry about how these things cancel out. The numbers that I multiply together are 1.94 times 2,500 times 3.28 cubed divided by 40 divided by 32.2, and that's equal one, 37771. Mind the significant figures there. Seconds. If I convert that to, say, days and hours or something, I'm curious to see what I'll get. So I'll just divide this by 3,600. That is 38.27 hours. I know I said I'm going to divide by 3,600. Of course, I'm actually multiplying by 1. Okay, so there's the calculation. It takes quite a while. According to this calculation, to fill this thing up, that is pretty significant. The takeaways, yet again, use standard units, get standard units. With more complex calculations, units can be challenging and confusing. So to avoid that confusion, we work out a way to not have to think about them. Just use standard units and you'll get standard units. If you trust that this equation is dimensionally homogeneous, then you know you'll get a time unit when you perform the calculation. And if you use standard units, you know the time unit that you will get is seconds. So that's that. If you have any questions, feel free to direct them to me. I will be physically in my office hours from 8 to 10, as well as holding them via Zoom conference meetings. So look up that information online. You can meet me in person or out of person. All right. Have a good week, everyone. I hope that you're staying healthy and calm. All right. Bye.